Well, the camera didn't work the other day, so I thought maybe it would be helpful for me to make a little video to kind of fill the gap. So, a couple things. First, I just want to discuss a little bit more about that formula I talked about the other day. So if we have V is span beta, W is span gamma, I want to just look at a formula we can derive for the dual basis and the basis, and so I'll use a little different notation here. I'm going to use I and J for the bases and dual bases of V. I'm going to use alpha and beta for the indices for the W and the W dual bases. All right, anyway. Getting to the point here, we could write x like that, right? That's the coordinate, ith component of x. Likewise, I can expand any vector in W with the coordinates based on the W dual basis. And so, for a linear map, I can derive the following formula. I can look at t of x is y, expand it in the W basis, and then I can take the y equals t of x, expand that in the V basis, pull the constants out, and rewrite things, identify what's going on here. Think about this x being fed to this vector valued operator. And if I do that, essentially going from here to here is a definition. But anyway, t has the following form. It's the sum over alpha and I, like so, W alpha, W upper alpha of this. Of course, that is the component of the matrix of T with respect to the beta gamma basis. Let me look at that on the next page here. Oops. I think I want my pages got out earlier. Sorry about that. Oh no, my rank-nullity showing. All right, so very briefly, we can define, the point of all this was just this, guys, is that if I want to, another way I could define the matrix of a linear transformation is in terms of the dual basis, and the dual basis of the range and the basis of the domain. Okay, that's the dependence. Is the alpha ith component depends on the alpha dual basis vector acting on the ith domain vector. And I put bars here because I'm talking about the barred basis. So what I'm doing here actually is changing coordinates to, I want to compare this to the corresponding beta gamma matrix. But to make sense of this, I need to first introduce coordinate change. So I guess my pages were not out of order, as it turns out. But maybe this helps motivate why I'm doing this. All right. So coordinate change. No, another way to look at coordinate change is just in terms of direct calculation. That's what I do here. And so this is, if I write the bar basis in terms of the initial basis and some set of constants, all right, then the fact that this duality condition between the dual basis and the basis gives me that, all right, and linearity, pull that out. But then I let Q be another set of constants such that the barred dual basis relates to the dual basis, like so. Plug that in, use linearity, and suffering through my notation here, pull out the QIL, get that, Kronecker delta, because this is again dual, right? This is equal to that. And that kills the sum over K or L. You pick it. I pick the K sum to survive. I set K equal to L, rather L equal to K. Get that. And then I looked at that and I go, oh, that's not quite a matrix sum because I need the, if I want to think about these being matrices and this being a matrix product and this, then I kind of need to make a little bit of an adjustment. Think about Q transpose, the Kith component of that. Then I got the K's matching. And of course, delta ij is delta ji. Long story short, I can think of Q transpose as being the inverse of the P matrix so defined. So we could express the transformation of the dual basis. Well, the dual basis transforms inversely to the transform of the basis is what happens. And if you study these things more carefully, you'll find out that this is actually the coordinate change matrix for the coordinates. I don't quite get to that point in this talk here, but anyway, I'm just starting down this. Here's a little consistency calculation to show you that, in fact, it works out. Like, if I put my newfound transformation law for the dual basis as it relates to the transformation law for the basis, well, basically 1 equals 1. Yay, check. High school proof. Aha. All right, moving on. Going back then, or forward, depending on your perspective, the coordinate, the beta bar gamma bar matrix of T, I could define in terms of the dual basis and the basis, like so. If I did that, and then I changed coordinates according to the rules I just found, all right, now here I'm introducing Q as the coordinate change matrix for the gamma basis, whereas P is the coordinate change matrix for the beta basis, as defined on the last page. Anyway, so I sort through that, pull the matrices, the changed matrices out. I get this, but this is, of course, the beta jth component of T beta gamma. And so you look at it, and we've got a matrix transformation law between the non-standard. It's the coordinate change relation. We looked at it a rather different way the other day, but in terms of my current notation, this is what it looks like. This changes to that, where I'm assuming that P is defined by this relation and Q is defined by that relation. All right. So anyway, I just wanted to show that to you. That's about all I have to say for now. We might come back to that later. We might not. Either way, it's okay. All right. So getting back to what I did last class, the rank-nullity theorem, let V and W be finite dimensional vector spaces over a field F, T a linear map, then rank of T is the dimension of the image, and the nullity of T is the dimension of the kernel. The theorem is that the dimension of V is the rank of T plus the nullity of T. All right. Let me go through the proof that we went through in class rather quickly here. So we start by noticing kernel is a subspace of V, and so there's a basis V1 through Vk for the kernel of T. And if the dimension of V is n, if I put r equal to n minus k, then I can extend the basis of kernel T to a basis of V by adjoining vectors v bar 1, v bar 2, v bar r, which are not in the kernel of T. And I'm going to denote that basis by beta. So beta has vectors not in the kernel, followed by vectors in the kernel, like that. Then I decided I would look at x and v. So this is a slightly different format than we did in class. Of course, the proof that was given in class was perfect the first time through. There were no errors made. There is no video record of that lecture, so who can say what happened there? Sorry. Anyway, excuse me. If x is written in the beta expansion, so there's the piece which is not from the kernel, the piece which is from the kernel. When you feed that to T, of course the kernel piece goes to 0, and the other piece remains. And this shows that, in fact, these guys, T, the image of v bar 1 through v bar r, that set of images, a subset of W, but also a spanning set for the image of T. So to show that that's a basis, we need to show that that's actually also linearly independent. And so we should suppose we have a linear combination equal to 0. Let me scoot this paper up here a bit. So we do that, but then by linearity of T, I can pull the linear combination inside, which then shows that this guy is in the kernel of T, right? And then that means that there exist constants such that I can build this vector from the basis for kernel T, which is the v1 through vk. So I have this equal to that, but then rearranging gives me this linear combination equal to 0, but then by linear independence of the basis, we deduce that all of the coefficients here are 0, which in particular tells me that the c bar 1 through c bar 8 are 0, which is to say we have shown that this set right here is a linearly independent subset of the image and hence is a basis for the image. So then the theorem is just counting. In conclusion, the nullity of T is the dimension of the kernel of T, which is the number of vectors in the basis for the kernel, which was K. The rank of T is the dimension of the image T, which is the number of vectors in the basis for the range, which I've called R. And you notice introducing this R made the proof easier to follow, didn't it? Hence, the dimension of V is n, but it's also n minus k plus k. N minus k is by construction R, and this is it. Dimension of V is rank T plus nullity T. So there you go. See, it's not that bad if you just go through it cleanly. All right? Now, the corollary, of course, to that proof is that we can construct basis beta gamma to put the matrix of T in this form, right? So if I just use the basis that I just talked about in the proof, and I take that basis for the range and I extend it by adjoining WR plus 1 through WM, then these guys, of course, they're not in the image, which means that under T they must be mapping to 0. So that gives us this matrix. Here's the details. We went through those, right? So like, this is by definition E1 because the gamma basis has that as the first thing, has that as the rth thing, so it gets us an R by R identity matrix padded with zeros, right? Finally, I would just mention that there's another way to look at this. We could steal this result from row reduction calculations if we were so inclined. Here's a picture to think about it. We have T goes from V to W. So the kernel of T is a subspace of V. The image of T is a subspace of W. I can look at the beta coordinate map, and that will map the kernel of T to the null space of the matrix. The gamma coordinate map in the codomain will map the image of T to the column space of the matrix T beta gamma. All right? And then the thing is, the coordinate maps are isomorphisms. Those preserve dimension, right? They take a basis to a basis, in fact. So we already know that the number of columns down here is equal to the dimension of the column space plus the dimension of the null space. But the dimension of the null space is the dimension of the kernel, and the dimension of the column space is the dimension of the image, therefore rank nullity. So here is another way to prove rank nullity theorem using the rights and privileges guaranteed to us through the study of isomorphism and the fact that the coordinate maps are isomorphisms which preserve dimension. So the fact that we already knew the corresponding rank nullity theorem for matrices, which was a direct corollary to row reduction, that's kind of neat. On the other hand, I like what we did in the previous 10 minutes because it gives us a proof which is independent of row reduction and just is about basis extension. So basis extension theorems and row reduction are hitting the same theoretical, they're scratching the same theoretical itch, so to speak, but they look so different, don't they? Okay, so now I'll talk a little bit about quotient space. I introduced this concept last class. I just want to run through here some of the background that I didn't have time last time. Let's see here, get straight to it. So we defined a coset for a subspace. X plus W is a coset. So like, I have W as the span of 1, 0. Here, let me draw some pictures while I'm doing this. So for this example, 7.8.2, W is, let me draw a picture here. Here's R2. What is W? It's span of 1, 0. That is, of course, the x-axis, right? This is W itself. So like up here, a parallel translate of that would be x plus W. Now x is a vector, so maybe I should say x1, x2 plus W. All right. The thing is, on that coset, I could also look at, say, x1 plus anything, anything. There you go, comma x2 plus W. That would still be on the same coset, right? Because the cosets here are just horizontal lines. Let's see here. If, moving on here, maybe I can, what have I done? Where's my paper? Lost my paper. Do I have more paper over here? I do. Woo! All right, moving on. Another example, which I can't probably picture, is if we had the set of symmetric matrices, we could look at cosets of those. So here's the theorem I mentioned: x plus w is equal to y plus w if and only if x minus y is in w. So the proof is right here. If we suppose they're equal, that means that if we have a point in 1, there exists a w such that p is x plus w1. But we also know that this is a subset of that, which means that there is x plus w1 is an element of y plus w, which means that there exists a w2 such that x plus w1 is equal to y plus w2, which means then that y minus x is w1 minus w2, but this is in the subspace again because w1 and w2 are in a subspace, and subspace is closed under subtraction. And there you have it. That shows that this implies that. And the reverse direction is very much the same. Let's look at it. If x and y are in V, and x minus y is in W, so I'm assuming that, right? Then there exists W for which x minus y is equal to W. So we could say x is equal to y plus W, or we could say y is equal to x minus W. If we pick a point in x plus W, that means that there's a W1 such that p is equal to x plus W1. But I can take that x, right, and I can rewrite it as y plus w1. So I get p is equal to y plus w1 plus w, which is, of course, in, because this right here, let me underline it, this right here is an element of w, so by definition this is in y plus w. So we've just shown that x plus w is a subset of y plus w because we took a point in this set and we showed it was also in that set, which proves that that's a subset of that. And by an entirely similar argument, we can prove the other direction, which is to prove that x plus w is equal to y plus w. So there you go. That's the proof of proposition 7.8.4. All right. And then, up next here, if V is a vector space over F and W is a subspace of V, then x plus W is equal to W if and only if x is in W. All right. So probably could even prove that with the last proposition if I was lazier, right? So 0, like, think about this. X plus W equals to 0 plus W, right? If and only if what? X minus 0 is in W. So really, if you could just prove that 0 plus W was equal to W, then you'd have proposition 7.8.5 as an immediate consequence of 7.8.4. But for the sake of trying to help you guys understand these kinds of arguments, I've gone through a separate proof of this again, which I'm going to skip through, okay? So anyway, the long story short here is that this construction of coset allows us to define, I can't see where I am. Stand up here for a second. Allows us to define, if we have two cosets, right? If I have, two different representatives of x1 plus w is equal to x2 plus w, and y1 plus w is equal to y2 plus w, then good news, x1 plus y1 plus w and x2 plus y2 plus w are equal, and also a constant times x1 plus w is equal to a constant times x2 plus w. This is important because this proposition is what we need in order to define the vector space structure of coset space here in just a second. So here's the proof. If we look at the difference, we already know that the difference between x's and the difference between the y's is in w again by assumption in the previous proposition. So if we look at the difference of x plus 1, y2, and y1 plus y, x1 plus y1, and rewrite that as difference in x's plus the difference in y's, well, that's wx, that's wy. And because these are both in w, this is again an element of w, which of course implies that, x1 plus y1 plus w is equal to x2 plus y2 plus w by the proposition 7.8.4. All right. And the proof of the scalar multiplication is very similar. So what that means is then we can define quotient space without ambiguity, because we've just shown that addition of coset representatives is unambiguous. So we say V mod W is the set of cosets, and we define addition by adding representatives, and scalar multiplication by multiplying representatives. All right. And indeed, you can prove that this operation gives V mod W the structure of a vector space. Here are the gory details. First of all, if we have two things in the coset space, you add them together or scalar multiply them, you again have something in the coset space. So at least axioms 9 and 10 are true. Axiom 1, commutativity of addition. So this is equal to that, is equal to that, is equal to that. So vector addition in the coset commutes. How about associativity of addition? This plus this plus this is this plus that, right? Which then is x plus y plus c plus w, which by associativity in the original vector space is that, and then you just unfold what we did the same way. And in fact, all of the axioms are kind of this. We just directly steal from the corresponding axiom in the vector space itself. 0 plus w is w means that w itself serves as the 0 in the coset space. All right. So I'm gonna go on here, but indeed, V mod W is a vector space over F. All right, called the coset space. Now, the notation that's nice to use, especially for the following examples, is, bracket x is x plus w. Another way to look at this, of course, is that we could say that x and y in the vector space V are equivalent if and only if this is true, right? Which is if and only if they have the same cosets, right? What I'm trying to say is that we can view the cosets, the partition afforded the vector space by the cosets, as corresponding to the equivalence relation that 2 points in the vector space are equivalent only if they are in the same coset. But anyway, I digress a little bit. Not too much, though. Anyway, in the notation, the bracket notation, let me get rid of this. In the bracket notation, we have that this is that, and c times bracket x is cx, all right? So here's some specific calculations. If we look at R3 with W being the z-axis, then the cosets are actually vertical lines. You could picture them like this, like here's the point A, B, 0, and the coset is like this stalk through there. All right. In other words, it's A comma B comma 0 plus W here. Well, that's interesting. My door just randomly opened. Here. All right. Next example. That was example 9. Example 7.8.10. All right. I have W is the, let's see here. What do we got? W is the span of basically I hat and J hat, if you like Calc 3 notation. In other words, this time, this is W. All right. In R3, it's the XY plane. And so like a typical coset would be something like this. Let's see here. This could be, like that point right there would be 0, 0, C. All right. So in this one, and this would be 0, 0, C brackets, if you like, or 0, 0, C plus W. It's the it's the horizontal plane that is parallel to W. So like the cosets in 7.8.10 are horizontal planes which you know, slice up R3. Each one of those horizontal planes can be labeled by its z coordinate. This is, you know, the coset space here is a set of vertical lines, each one of which can be labeled by its intersection with the xy plane, right? So maybe you start to gain a sense that the coset space here is two-dimensional, whereas the coset space here is one-dimensional. I'll make that precise here in just a second. You can also talk about polynomials and look at the coset of those. I'll let you read about that. I'm going to go ahead here. Maybe I'll talk about that in class today, I don't know. So that brings us to the first isomorphism theorem, all right? Wait a minute, I feel like my pages got out of order. No, they didn't. My bad. So we introduce, let me get rid of my page there. So we introduce the first isomorphism theorem, which is stated in terms of, among other things, the quotient map. The quotient map goes from the vector space to the coset space defined by, basically just maps x to its corresponding coset, x plus w. All right. You can prove that that's a linear transformation. Here's the proof. It's not hard. Pi of cx plus w is cx plus, pi of cx plus y is cx plus y plus w by definition of pi, which by definition of coset addition is this, which is by definition of scalar multiplication of cosets that, which is by definition of pi c pi x plus pi y. So pi is a linear transformation. And what's its kernel? Well, the kernel of pi would be everything that maps to 0 in the coset space. What's 0 in the coset space? Well, we just talked about it. It's w. So the kernel of pi is w. And that actually plays a special role here in the first isomorphism theorem. Here it is. If T, going from a vector space V to a vector space U, is a linear transformation, and W is the kernel of T, then the quotient map pi, and has quotient map pi, all right, then the mapping T bar, which goes from the coset space V mod W to U, defined implicitly by T bar composed of pi equals to pi, is an injection, which means it's 1-to-1. Furthermore, T bar of x plus kernel pi is equal to Tx. This is just a formula which means the same as that, all right? This formula right here is meaning this equation, all right? And, but we also have the following, that the quotient of V by the kernel is in fact isomorphic to, sorry, my notation has gotten better, is isomorphic to the image of T. This is image of T is also, right? Image of T. All right. Now, the proof of the first isomorphism theorem is given below. All right. So first thing to do is to show that it's in fact well defined. So T bar, well, T of x, right, is in U by construction. And so since T bar is into U, let's see here, so T of x, if, let's see here, well, here's the formula. This is the definition right here for T bar. T bar of x plus kernel is T of x, right? So certainly T of x is in U, which means that T bar defined by this formula is definitely taking U as its codomain. That's fine. Into just means that the formula at least makes sense, that the codomain is the codomain. Is T bar single valued? Well, suppose you had two different representatives of the coset. X plus kernel T is equal to Y plus kernel T, right? That would mean that Y minus X is in kernel T, which would mean that T of Y minus X is 0, right? Which would then give us that T of X is equal to T of Y, but that's what we need, that this formula is independent of our choice of the coset, the kernel coset. So that shows that the mapping is well defined. Next, notice that I'm still, sorry, I need to scroll down a bit. So it's single valued, right? So it's well defined. Next, of course, I need to show it's a linear transformation. Here's the proof of that. T bar of this plus that is, by definition, of coset addition T bar of this, right? But then by the definition of T bar, it's T of the representative, which then by linearity of T gives me that. And then unpacking it, this is C of T bar of x plus w, and that's T of T bar of y plus w, which proves, of course, linearity. And finally, we turn our attention to injectivity. If I have x plus y and y plus x plus w and y plus w in the coset, is it equality of T bar under these inputs imply that the inputs are the same? Well, if this is equal to that, that means that T of x is equal to T of y, which means that T of x minus y is 0, which means that x minus y is in W, which is the kernel, which then by our previous proposition proves that, in fact, yes, the inputs were equal in the coset space. So that proves that T is injective. And finally, the isomorphism, well, that just, if we have a linear map which is injective and surjective, then it's an isomorphism, right? So the surjectivity is given because we're letting the T prime be the mapping which is given by T bar with the codomain swapped out for the image. So we're taking U and replacing it with TV. That makes T prime into surjection. And of course it's also an injection because we just proved that. And the details aren't different if we replace the codomain U with the codomain T of V. So that proves that this T prime so constructed is an isomorphism, which then of course proves that V mod the kernel is isomorphic to the image. And that, my friends, is the first isomorphism theorem. And here I have some examples of the first isomorphism theorem. I'm trying to prove that V cross W quotient by 0 cross W is isomorphic to V. If we look at the linear mapping T of VW equals to V, it's easy to show that the kernel of this is just 0 cross W. So then the first isomorphism theorem says that V cross W mod the kernel of T is isomorphic to the image of T, because, by the way, it's easy to prove that the image of T here is all of V. Okay? I'm trying to put equals on those. Sorry. All right. This next example, it's got a little bit more depth to it. Here I look at the mapping A plus A transpose. You could call this the symmetrizer of a matrix. It takes any matrix and replaces it with a symmetric matrix. Although I think usually people would divide by 2 to get the symmetrizer. But it's easy to prove that the image here, SA, is in fact symmetric, right? And it's also onto. You take any matrix that's symmetric and you look at A over 2, it maps to A. So S is a surjection onto the set of symmetric matrices. And what's the kernel of S? Well, it's also easy to prove that the kernel of S is antisymmetric matrices. So the first isomorphism theorem says n by n matrices mod the kernel of S. In other words, n by n matrices mod the antisymmetric matrices is isomorphic to symmetric n by n matrices. So that's kind of neat. I think directly constructing an isomorphism from the quotient space of n by n matrices mod antisymmetric matrices to symmetric matrices would be much more challenging for you guys, right? And then here's a polynomial example, which I probably should talk about in class a little bit. Actually, I think I'm just going to let you read it. If there are questions about it, I'll come back to it. This is, again, about the polynomial. Well, I think I'm going to let you guys read these here, and I'm going to stop this video here just to not go too long. I want to start next time. Maybe we'll look at this theorem in class today and go from there. So, thanks, guys.